Okay, so we've covered the Metropolis algorithm with the symmetric proposal. We covered the Metropolis Hastings with the non-symmetric proposal. And we talked briefly about using the Metropolis algorithm or even Metropolis Hastings algorithm for a multidimensional case. And in the multidimensional case, you just need a multidimensional proposal. And that's fine, except that sometimes with a multidimensional proposal, you just end up rejecting a lot of values, okay? And in that case, your algorithm will run quite inefficiently, and that's not a desirable trait. And so we have there's an algorithm called the Gibbs Sampler, and this helps us to sample from a multidimensional distribution, right? Okay, so this is what we want to do. Okay, Gibbs Sampler. This is a way, allows us to sample from a multivariate or multidimensional distribution. Okay, in an efficient manner. And I would say in Bayesian statistics, when you have multidimensional models, which is pretty much almost all of them, okay? Very rarely do you deal with just a unidimensional model, except for these toy examples of flipping coins and things like that. Most of the time, you're dealing with, multiple parameters that you're trying to estimate, things like that. You're almost always dealing with a multivariate dimensional, or a multivariate distribution. Sometimes you have very high dimensionality, and because the Gibbs sampler is efficient, it's a very popular choice. Okay, a very popular choice. In Bayesian statistics. The requirement is that we know the conditional distribution of each variable if the other variables are known. Okay, in order to do Gibbs sampling, so we need to know the conditional distribution of a parameter, or conditional distribution of we'll say of a variable given all of the other variables in the distribution. Okay, so for example, let's say we have just a simple, if we have 3 dimensions, or 3 dimensions or 3 parameters, 3 variables, theta 1, theta 2, and theta 3, okay? And we wish to sample from the joint distribution of all 3. Joint distribution of all 3. And that would be, density of theta 1, comma theta 2, comma theta 3. This is what we want to sample from. Okay, and maybe we know this, maybe we don't. Okay, and especially if it's like you know, in the Bayesian context, it might be we want to sample from the posterior given the data. Okay, so I'll say, you know, in a Bayesian context, you know, maybe we might want to sample from theta 1, theta 2, theta 3, given the data. Okay. All right. So this is what we want, and perhaps perhaps the complete. This is what we would call the complete joint distribution, or the complete joint posterior distribution, if it's in the Bayesian context. This might be complex. Okay. The form of this distribution might be complex. Maybe not, but it might be complex, and maybe it's really hard to draw, you know, all three values together at the same time. So with the Gibbs sampler, what we do is we create conditional distributions for each of the parameters. So instead of trying to sample directly, from this distribution, you know, we find the conditional distributions for each variable. So we will need, so we find theta 1 given theta 2, theta 3, and the data. And then also we find theta 2 given theta 1, theta 3, and the data. And we find the conditional of theta 3 given the other ones, theta 1 and theta 2, and the data. Okay. Or, you know, in just a generalized context, you know, this is in the Bayesian application where the data is part of what forms our distribution, but you know, basically this is what we do. Okay, and then so we say perhaps so this is there's a strong assumption here that we can get the form of this, and that we can figure these out. Okay, and you know, the hope, and this is often the case, especially if you have some kind of system, you know, explaining where each of these things come from. The hope is that each of these conditional distributions is much easier to that we can generate values from these, and these are easier to understand. Okay, so you know, the hope and ideal case is that each of these conditional distributions are much simpler than the joint distribution. And ideally, it is also, and we can generate random samples from each conditional distribution. That's what we're hoping. Okay, and if that's the case, then the Gibbs sampler will work very well. Okay, if we can't figure out the conditional distribution for the thing, then the Gibbs sampler is not a good pick, because the Gibbs sampler requires that we can get these conditional distributions. Okay, and so perhaps maybe just a reminder of what the conditional kind of the conditional probability. What is the conditional probability? So the probability of A given B is equal to the probability of A and B divided by the probability of B. Okay, so in this case, the probability of kind of theta 1 given theta 2, theta 3, and the data would be equal to the joint, the probability of theta 1, theta 2, theta 3, and the data divided by the probability of theta 2, theta 3, and the data, right? Okay, and then so the numerator can be thought of as, or if we make everything conditional on the data, we can also just say this is theta 1, theta 2, theta 3 conditioned on the data divided by the probability of theta 2 and theta 3 conditioned on the data. So that's also an option, right? So we can condition everything on the data. This is kind of the total joint posterior, and this is just the kind of the marginal of the we integrate this out. So total joint posterior and this is kind of the marginal distribution. So this is effectively just we integrate out theta 1, or sum across all values of theta 1 there. Okay, anyway, let me go back and we'll do kind of just a 2D example. And so this is we'll do a two-dimensional example. So we have theta 1 and theta 2, maybe given our data, we have some posterior distribution. For 2 dimensions, or 2 variables. And we will get, and so just the way the Gibbs sampler will work is, we begin with some value. Okay. With a pair of values. Theta 1 at time 1 and theta 2. We'll say at time t, and theta 2 at time t. And what we do is we look at the conditional of theta 1 given theta 2. So we say, we're going to look at theta 1 given theta 2 on the data. And we're going to just, and we draw a sample. We draw a single value from from here. Okay. And so this will be theta 1 at time t plus 1. So actually, let me expand this. We condition based on theta 1, and this is given theta 2 equal to theta 2 at time t in the data. And we draw a single value from here. And then we get the other conditional, and we're going to take theta 2 given, and now we look at theta 1, and we set theta 1 equal to theta 1 at time t plus 1. Whatever value we drew from here, we set that, we condition it on that, and we get this, and then we just repeat. So and then we draw theta 2 at time t plus 1 here. And then we go back and forth, and we will get theta 1 given theta 2 is equal to this new value. And then we draw theta 1 at time t plus 2, and then so on and so forth. Dot, 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 dot. Okay, repeat. And so, and if you have more than 2 variables, then you just cycle through them. You draw theta 1 given theta 2 and 3, or given everything else. Then you go to the next variable given everything else, and then you go to the next one given everything else. And every time you draw one, you just update everything that's been given here. Okay, so you just use the latest value that you have, and you just update kind of the list of the values that you have, and you condition on those, and then you just draw values from there. And this is technically it's a form of the Metropolis. It's like a special case of the Metropolis-Hastings algorithm, except there's no we don't reject any of these values. We accept every single one. Every single one we draw, we accept as a draw here. Okay, and you say, well, how does that even work? Okay, well, the idea is that when we condition based on the other things, this thing that we are drawing from is the exact form of the posterior distribution. So it's like we are drawing directly from the posterior, but we're only drawing from the posterior. We are drawing directly from the posterior, but only for a certain slice of the posterior, if that makes sense. Okay, so I'm going to go to our textbook and just draw the picture because their picture is good, and so. Okay, so here we are. Let me see if I can. Okay, so the entire shape is our joint posterior. Okay, so the entire three-dimensional shape is the joint posterior on theta 1 and theta 2. Okay, what we do is when we're going to condition, we say theta 1 given theta 2 is equal to some value. Okay, and technically the data is in here also, right? This is our posterior. So this is our entire 3D shape. This is what we have given the data. And we say, oh, okay, when we isolate it, right? If we say theta 2 has to be this exact value, this is theta 2 is equal to some value. Now we just have a one-dimensional, a unidimensional distribution. Okay, so now we just have this. Okay, so this is the probability of theta 1 given theta 2 equal to theta 2 at time t and the data. Okay, and if this is a known form, we can generate a random value from here. Okay, so we draw a random value from here. Okay, and it looks like it's right here. Okay, so we draw a random value, and this is going to be the value that we use next. So this value is going to be our theta 1 at time t plus 1 at the next iteration. So we draw a random value, that's what we use. And we accept this, okay? We don't have to worry about, is this better or worse than my current thing? Because this is the exact form of the posterior distribution for that value of theta 2. Okay, so we accept our whatever value we draw from here, because this conditional distribution is exactly equal to the posterior distribution. Okay, exactly equal to the distribution we want, just conditioned. So it's like we are drawing directly from that distribution, just conditioned on it. Okay, so this is technically our proposal distribution that proposes the next value, but because it's exactly what we want, we're just going to accept it. Okay, so this is technically our proposal distribution, but it's exactly what we want, so we accept it. Okay, and so once we've accepted this, this is going to be set the distribution for the next iteration. And so the next iteration, okay, we've drawn this value, okay, and so we condition right here at this value of theta 1. And now that we've conditioned at that value, we have a new distribution for theta 2, given theta 1. Okay, so this is our distribution of theta 2, given theta 1 is equal to whatever value we drew last time at time t plus 1 and the data.
Miles?
Yes.
So since the proposal distribution is exactly like the distribution that we want,
yeah.
Like for when we do these like unidimensional sampling methods, we use a proposal distribution that's easy to sample from.
Yeah.
So this is assuming that the conditional is easy.
Right. That's part of the thing with Gibbs. There's Yeah, so earlier on, I think at the beginning I said in order for us to use Gibbs sampling, we need to know the form of these conditional distributions. And there's also the assumption that drawing a sample from the conditional distribution is easy.
So if the conditional distribution isn't easy, we can make a preferable distribution that's like.
Yeah, so then if the conditional distribution itself is not easy, then you might have to use another method to draw a sample from that conditional. Okay, and so yeah, it's oh, you can kind of like mix and match the pieces to get everything together. So in the ideal scenario, each conditional distribution has a nice form and is easy to sample from. So you go, parameter 1, nice form, I'm going to randomly sample it, I accept it. Now I move to parameter 2. I set up the conditional distribution, it has a nice form, I randomly sample from it, I accept it. I go on to parameter 3, I set up the conditional, nice form, sample it, okay? That might not always be the case. And then so perhaps variable 1, easy form, we randomly sample, and then we accept it. Parameter 2, crazy form, okay? So we set up the conditional distribution. Maybe the conditional distribution has a difficult form, and so perhaps we have to resort to acceptance rejection sampling.
Yeah.
Okay, or some other method to sample from this weird form. But basically, the idea is we draw from the conditional distribution, and then when we draw from that conditional distribution, we're going to accept it, and then we move on to the next one. So, and then sometimes you might get like a 2-in-1 bonus, right? So it may be the joint distribution, the conditional distribution of 3 and 4 together. Like maybe you have variables 3 and variables 4 together, and maybe variables 3 and 4 turn out to be a multivariate random normal, which you're like, oh, that's not so hard to generate from. So maybe you can generate both of those variables together. And then you've killed 2 birds with 1 iteration there. Okay, and so if you have like 20 variables or something, you might be able to mix and match and find different things for each one. And as long as you can account for a conditional distribution of some kind for every single one, you build everything up, and then you just kind of cycle through this Gibbs sampling step. It sounds a little crazy, but it works, and it's a very popular method just because of the efficiency here, in that we're not rejecting so many things. I mean, perhaps for one of these we have to use an acceptance rejection form to do it, and then you might have a rejection rate, but just for that one variable in the set of 20 or something like that. Okay, so anyway, we do this, we get theta 2, we draw from this sample, we draw theta 2 from this distribution. Okay, and then we condition on this, and then we go back and we repeat. We go back and sample theta 1, and so on and so forth. All right, and so if we were to take a look at the way the Gibbs sampler works, it will look a lot different than kind of the Metropolis algorithm. So let me, the illustrations in this textbook, I'm a big fan of them. Let's see. Okay. So which one is the Gibbs and which one's the Metropolis? Okay, so this one is Gibbs, and this one is Metropolis, right? So let me maybe this didn't work, didn't make sense. Okay, so after many iterations of the Gibbs sampler, we're going to end up getting something that looks like this. All right. So if this is what we see here is that when we condition on each variable, okay, when I say we're locking in a certain value for theta 1, now it's just a vertical line that we have a unidimensional distribution that we proposed from, okay? So the next value we propose for theta 2, will be somewhere along a particular value for theta 1, right? So let's say if this is theta 1 at time t, we're basically just we're picking a value here, and perhaps we've sampled right here, okay? And so this becomes theta 2 at time, I don't know, at the next one, t plus 1, and then now we're doing a search basically along here, and then we draw a random sample, and perhaps it ends up right here, and so then we draw along here, and we draw a random sample, so on and so forth. Yes?
So then, with theta 2 at time t, what would that represent?
So it's just an arbitrary starting point. You just start somewhere, and then, so...
I think if we're starting with theta 1 at t, would it...
Yeah, maybe I counted this backwards here. I guess this would have been theta at t. I probably should have started off at theta 2 at time t. We sample from that, and then we draw from theta 1.
So t has two values to assign, in a sense.
Yeah, no, at time t, yeah, you have a theta 1 and you have a theta 2, and then during the next cycle, you're going to generate a new theta 1, that'll be t plus 1, and then once you have that, you use that to generate your next theta 2, so on and so forth. So here, basically, we are moving through one dimension at a time. So with Gibbs sampling, we update one dimension at a time. Okay, and then on the other hand, with the metropolis, the multivariate metropolis, we try to update all of the values at the same time. Okay, multivariate metropolis, we update all of our parameters at the same time, or metropolis Hastings, okay? We update both, or in, all variables at the same time. Okay, and so with the multivariate metropolis, you're going to move in both directions or both dimensions, and so now you get kind of jumps around the place. Okay, and the values that come from here and the values that come from here, as long as you've run it long enough, will both be random samples drawn from the target distribution that you want. Okay, so both methods generate values from the target distribution. Okay, it's just with the multivariate metropolis algorithm, because each proposal now consists of multiple coordinates, if one of those proposed values is in an area of very low probability, right? So if you have like 5 dimensions that you're going through, perhaps, based on your proposal distribution, you might propose something where theta, variables 1 through 4 each have high probability, but because of random chance, the 5th variable ends up in a region of very low probability. Okay, and in that case, the overall probability of that coordinate is going to be very low, and so when you compare the proposed probability versus the current probability, it's going to be quite low, and there's a good chance it will be rejected. Okay, and you have this problem with the multivariate metropolis unless your proposal distribution is very, very good in terms of matching your target distribution very well. But I mean, if that's the case, then you might as well try to sample directly from the target distribution. So again, the idea here is with Gibbs sampling, perhaps the joint overall distribution is a little bit complex, but we can simplify them into just single unidimensional conditional distributions, and each unidimensional conditional distribution is easier to sample from. And then because the unidimensional conditional distribution is directly of the form of the posterior, we can accept every single value we propose. So it becomes a lot more efficient in this regard. Okay, so this is kind of just the a high-level overview of Gibbs sampling, and then I think on Friday we'll code some of this up and see this actually running, and I don't know, maybe it will be of interest or not. And then yeah, I've got to think of homework 4 for you guys, so that's in the works too. All right, we'll end here, and then we'll see you guys on Friday.